Hey guys and ladies, gentlemen. We are going to start with the notes from class. So if you haven't done A, B, and C, I highly suggest you pause the notes and do them now. As you can see, we are going to pause the video and correct it. So here is A. You can tell that I rewrote the equation because let's be honest, I don't want my x following, I should say, a number. That's not what I'm used to seeing. So you can absolutely rewrite the equations as long as you maintain whatever their sign is. So if it's positive, they're positive and so forth. Okay, I have the parent function table here, transformation chart here, and then I graphed it with the transformation language below. All right, so go ahead and pause, check B. Okay, so you'll notice for B that it's not, we didn't actually have to move anything around, but we did have to factor out the B volume. What? B value. So you'll notice, again, we have the parent table, we have the transformation table. It is not only horizontally compressed, but vertically stretched. So you'll notice that we can't really graph a whole lot of this. I did my best to put the curve at the central point, which is 1, -1. And now if you need to pause, so you can do the absolute value. And last but not least is C, which is our absolute value function. Now, I will not ever expect you to do an X and a Y chart. If you want to, you absolutely can. But things to note, we can easily find the vertex because it's HK. If there is a B value, you can address that as taking the absolute value of 1/3 as long as you've factored it out. The A and the B have the same effect on this particular function for two reasons. Number one, it's symmetrical. Number two, it is a constant rate of change from one point to the next on either side of the vertices. So that's how I got down to here. And there are our three that from class. If you need to pause the video, please do so you can go over it. I am moving on for this next part. Various implications. This is a practice for you, okay? My suggestion would be to write out the parent table. The first point is at pi over 2, 1. And then the second point is at 3 pi over 2, -1. And then our third point is at 5 pi over 2, 1. Well, look at what each of these examples is going to affect. This has an A value. That's going to change our Y's. It's going to stretch them. This is a B value. So we're going to multiply our B's, our X's, by the reciprocal of B, which is 2. So it's going to affect the X's. This one is an H value. So it's going to affect the X's. We're going to add pi over 2. And then for this one, we not only have an A, a B, an H, and a K. We have all of them. So you're definitely going to need to factor out that B and then go from there. What I would like for you guys to do is to take these points and apply the transformations for A, B, C, and D. Okay, go ahead and do that. If you'd like to see the answer key, please let me know. I will absolutely show it to you. We are moving on. All right, so find the function that's finally graphed. So we're told that f of x equals y, and both of those are displaying a function of the square root of x. Well, what I'm going to do, because this is interactive, is I'm going to give you a minute or so, and I want you to write what the function's going to look like after the different shifts and stretches. Okay, so for example, I'll do 3 first. An x-axis reflection. Okay, that means that your A value is being multiplied by -1. Up 5. That means that K is a positive 5. So for this particular one, I'm going to write that f of x is equal to a negative square root of x plus 5. Because remember, if I'm in generic form, f of x is going to be equal to a times the square root of b times the quantity x minus h plus k on the outside. Okay, so I'm going to pause the video. I want you guys to pause it and attempt 1, 2, 4, 5, and 6, and then hit play and see how you do. How do we do? Take a look. A couple things to note. The h value is the opposite sign, right? So we had to think about that with numbers 1 and 4 and 6. So take a look. The only thing I could think to point out besides that was if we're going to horizontally stretch or compress, which we're doing here, you have to apply it as the reciprocal, right? So if I'm compressing by a factor of 1/3, that means that there is a 3 in my given equation, because the reciprocal is what determines, what sets the compression or the stretch. Okay, for 6, I'll accept either, whether you want to leave it factored out, which I think is probably the easiest, but some people like to factor it in, and that's fine too. Okay, for our notes that we started in class, these are the last pieces. These I think are the most fun because they're so simplistic, but you really have to understand the concept. So it's definitely a puzzle. I'm a puzzle girl. So for the example, we'll just call it, well, this guy. All right. If 2, 5 is a point on the graph, okay, so that's x and that's y. And we don't care what the function is, it's a function. Okay, we're told that. It doesn't matter. We know that this point exists on a function. Find the point that must be on the following graph. Okay, let's look at it one by one. For this, there's a negative on the inside, which means that our b is negative. Okay, I'm going to write that down so I don't forget. B is -1 times b, which is affecting the x values. This is really testing if we understand our transformations. So if b is negative, that means that it's going to multiply all of, if you think about your transformation chart, okay, plus or minus h, and then we have ay plus or minus k, right? I'm going to erase it because we don't need it, but just a visual reminder. Then that means our new point would be -2, 5. And that's all it's asking you for. Why? The negative was on the inside. It means that our b was negative. Therefore, all of our x values are going to get multiplied by a negative. Okay. What about b? 3 is on the outside. So that means that our a value is 3, which affects the y values. Nothing's going to happen to our x's. Again, 1 over b times x plus or minus h, ay plus or minus k. Okay? So if there's an a value, we multiply it to the y's. So the point 2, 5 that was originally on our function, well, the 2 stays the same, but the 5 gets multiplied by the 3. So the new point would be 2, 15, and that's all it's asking you. If these transformations are applied to the given function, regardless of what it is, and this point, 2, 5, is on the given function, where is the new point going to lie? That's it. Easy peasy. All right, well, what about the next example? Suppose that the x-intercepts of the graph, again, I don't care what it is, it's f of x. It is some function. What its function is doesn't matter to us. What matters is that we are given x-intercepts. Okay, that is key. So the x-intercepts are -6 and 2. What does that mean to us? That means we have a coordinate at -6, 0, and 2, 0. What are the x-intercepts of the graph? Okay, well, the first example for A is f of x plus 3. So we have to ask ourselves, does this affect the x coordinates of the graph? Because if it doesn't, it's going to stay 0. Remember, x-intercepts, right? Our y values are 0. We're asking, what are the x-intercepts? So does each of these transformations affect the x coordinates? Well, this one I'm going to put as a yes. And it's going to go 3 units to the left because there's an h value. So what we're going to do is we're going to take each of these x-intercepts and we're going to subtract 3. Why? Because h is -3. So the new x-intercepts are at -9, 0, and -1, 0, all because the h affects the x's. Here, I'm going to say no, because this is an a value, and the a's that affect the y. What is 0 times 3? 0. So the x-intercepts stay the same. So we're just going to write -6, 0, and 2, 0. Those are easy. I know. All right, for C, yes, it affects the x values. How do I know? Because it's inside the quantity with the x variable. And this happens to be a b. b in the equation is -2, which then applies as a -1/2. So we're going to multiply every x-intercept, because again, up there, by a -1/2. So the first one's -6 times -1/2 gives us a +3. And then we have 2. 2 times -1/2 gives us a -1, so there's our new x-intercepts. Again, not super complicated, just really testing our understanding of the transformations and what they affect and how they affect. Okay, our last example for this note guide. Suppose we have a function f of x. Again, do we care what the function is? No, we don't. But we do care about the fact that it is decreasing on the interval -1 to 8. Those are x values. Remember, increasing and decreasing intervals are discussed by the x values. If you didn't know that, yep, you should definitely write that down again. We only say x values. So we're saying from x is -1 to x being 8, the y values are decreasing. If you need to write that down, write that down. We are saying from x at -1 to x at 8, okay, these are my x values, and this is a super simplistic idealization of it. My y values are decreasing. That's what it looks like, okay? So for A, it asks, over what interval is the graph of y equals f of x plus 1 decreasing? Well, x plus 1 inside means that h is -1. So it's going to shift all of the x values to the left. Since an increasing and decreasing interval is discussed by the x values, we're going to take these and we're going to subtract 1. So we're going to say that it decreases from -2, because -1 minus 1 is -2, to 7. That's the interval of space where this function that's shifted to the left 1 unit is decreasing. Okay, for B, over what interval is the graph of y equals f of x minus 4 decreasing? Well, this is an h, and it's a +4. So we're going to add 4 to the interval, because the interval is being discussed with the x values, and this affects the x. So -1 plus 4 is 3, and 8 plus 4 is 12. So we see, could I mess up more in this video? Sorry guys. We say that the function, regardless of what it is decreasing from 3 to 12 when the function is shifted 4 units to the right. Okay, C, what can be said about the graph y equals -f of x? Well, this is a vertical reflection because there's a -1 in front of the a value. So if I am decreasing, as shown here, and I vertically reflect, good, you are now increasing. So what can I say about this? I'm going to say that I am increasing, because I've reflected over the x-axis, from -1 to 8. Not only do we need to say that it has changed direction, but we need to discuss the fact that it's from what to what. Okay, it's from -1 to 8. And then, what can be said about the y's? Ooh, now this is interesting. Let's think about this. Sorry, this guy right here, y equals f of -x. Yes, it's going to absolutely change from decreasing to increasing because it is a reflection. This is b as -1. But it's b. b affects the x values. These intervals are x values. Dun, da, da. If you need to, write that down. When there is a reflection, the direction of growth or decreasing changes. But if it is a horizontal reflection, that means that our x values are also affected. So we are now not just increasing like we saw in C. We are now increasing from -8 to 1. Yep, The x values change their sign. We have to list it from smallest to largest. Awesome. Whew, that's a lot of good stuff. Definitely things we've known before, but I love how it forces us to delve into our true understanding. All right, one little piece left. I'm going to pause so I can switch and not waste your video time. Do me a favor and pause it and then grab the notes for lesson 1.5. And we're back. Okay. So some really important vocab, and I just went over it, but let's write it down. In order for us to discuss properties of functions, we need to really understand what all this means. Okay. Increasing. Increasing is an interval. Let's change this. A domain interval, because we deal with our x values. A domain interval. You can write x values if you want to, where the y values are increasing. So what we say for an increasing interval is from negative infinity to positive infinity. That would be our interval. And that represents that from negative infinity to positive infinity, our y values are increasing. Okay? Same with decreasing. It is a domain interval. A domain interval, that again is your x values, where the y values are decreasing. They're getting smaller. Decreasing. Okay. Constant. A constant function is where the regardless of input, so regardless of what the x value is, so regardless of input, which is the x value, the output is constant or the same, so the y value is the same. If you want to write down also a constant function or a constant piece of a function is a horizontal line. Horizontal line. There we go. Local maximum. Okay, local maximum is any, any y value where the function changes from increasing to decreasing. And yes, I'm totally abbreviating. Feel free to follow suit or write out the whole word. It is up to you. And a local minimum is any y value where the function changes from decreasing to increasing. There we go. And how do we write these increasing and decreasing, the maximum minimums? You would say y equals the number at, so what is the maximum, what is the minimum value, and where is it located? So y equals 7. That is my local maximum at x equals 2. Okay, you have to say what it is and where it can be found. And then our absolute maximum or minimum is the highest or lowest point where the function does not pass. So an excellent example of this would be a parabola. Its vertex is either the absolute maximum or the absolute minimum because it is the lowest most point or the highest most point. And the average rate of change is the change in the y values over the change in the x values. Change in the y values over the change in the x values. Many call this rise over run or slope. But be careful, we don't necessarily discuss this with exponential functions because they aren't constantly increasing at the same rate from one point to the other or constantly decreasing. Whoop, whoop. All right, ladies and gents, we have one example and one example only. Given this beautiful little graph here, find the domain and range. Okay, domain. Domain represents the set of all x values. If I look, the smallest x value is a -5, and it is a closed circle. So I'm going to say bracket inclusive -5. My function doesn't look like there's any holes. And it appears right here at 3.5 is where the x values will stop. So I'm going to do a 3.5 bracket because it's inclusive. Now, if there were any holes in the function, I would stop it, my domain in my listing. So maybe I went from -5 to 2. And then at 2, I have this big gap. But I picked up at 3. And I went to 3.5. This represents union, which means this and that. Both intervals of space are represented in the domain of this function. And that's just an example. Okay, so this and that. But thankfully, this is one continuous function. Continuous means that you can draw the function from left to right without picking up your pen or pencil. That is fantastic. Okay, and the range. Our range, again, smallest to largest. It looks like it is there. It is a closed circle. So I'm going to put bracket for inclusive -6. And looking up, oh, it looks like right here, it goes to 0. So that's the range of this particular function that we're given in graphical form. Where is it increasing? Okay, I'm going to increase, it looks like, from -5 to -3 with increasing and decreasing intervals. We only use x values, just like I talked about, x values. And we don't use brackets because I'm not talking about, oh, I got to this point and I'm inclusive. No, that doesn't matter. I want to know in what area of space in between which x values are my y values increasing. So this represents from -5 to -3, my y values are increasing. And then oh, it looks like they increase from 2 to 3.5. So we're going to say union, parentheses, 2 to 3.5. Again, we don't use brackets. We're not talking about including values. We're stating intervals of space to where the y values are increasing. Or, in this case, decreasing. Okay, it looks like from -3 to -2. Okay, so we're going to write that as our first, -3 to -2, union. I think 1 to 2. Those are the only intervals in which our y values are decreasing. So we have 2 intervals of increasing, 2 intervals of decreasing, and hello, we are constant from -2 to +1. Constant because regardless of what x value, I am always going to have an output of -3. Nice. Okay, so we were able to pull domain, range, intervals of increasing, decreasing, and constant y values just from looking at this graph. What about intercepts? Now that's x and y. Let's do x first. I only see 1, and thankfully it was written out for us. We don't have to guesstimate. So I'm going to say x-intercept is at -3, 0. As for the y-intercept, I only see 1, so we'll just list that one. Y-intercept at 0, -3. The next question about even, odd, or neither we haven't talked about, so we'll just put TBD, to be determined. That is coming at us on Friday, I believe, or Thursday, depending on what class you're in. And then at what numbers, if any, does the function have a local maximum and a local minimum? Okay, local maximum are any points in which the function changes direction from increasing to decreasing, and I only see one. I'm going to say that it is 0 at x equals -3. Again, what's the maximum and where does it occur? Okay, what is it? Where does it occur? It is 0 at x equals -3. Now, some would argue, oh, what about this guy? No, it doesn't change direction. I just get up to that point and then I stop. Now, does it have a local minimum? This one? No, because I'm not changing direction there. This one? Yes. At that point from left to right, don't forget, you read a book, you read a graph, left to right. So I'm changing from decreasing to increasing at that point. So yes, I'm going to say local minimum is -4 at x equals 2. What is it? Where does it occur? I say what is it because our maximum and minimum values are always our range values. Think about your height. How tall are you? I am 5'3" and 3/4 on a good day, but I'm getting older and I think I'm shrinking. So we'll just go with 5'3". So my maximum height is 5'3". I'm not going to talk about how much space I take up horizontally. My maximum height, right? So same idea with a graph, a function. What is your maximum? Now, local maxima, I'd like you guys to do me a favor on H and J. Change it to absolute. Just cross it out. Absolute. Okay, well, we only have one maximum value, right? One local maximum. Now, something to note, super important, you should probably write it down. You find the locals first. You could have one, you really could have none. You could have 7. The absolute will be a local. I'm going to say it again. The absolute max or min will also be a local. But you can't have an absolute that is not. Okay, we identify all the locals first. How many maximum points do we have? How many minimums? Which one's the absolute? Which one's the supreme? I'm the absolute ruler. Yeah, right. Okay, we're the supreme, the most, the highest. So let's look at our one maximum point, this guy. Does our function go past that value? No, that is the absolute maximum because our function does not extend past that point. So we say the absolute maxima is 0 at x equals -3. It's okay to have the local and the absolute be the same. In fact, they will be. All right, but what about the minimum? So here's our minimum, right, the local. Does the function go below this minimum point? And the answer is yes. This whole piece of the function is below this minimum. So, do we have an absolute minimum? No. No, we do not. We just write none. Okay, hopefully that was pretty clear to understand. We will start class with a review of this, and I'll see y'all later.